Dr. Zimmerman is the Donna Davinsky Associate Professor of Environmental Engineering, and she's jointly appointed in Chemical and Environmental Engineering Department at Yale University. And this is within the School of Engineering and the School of Forestry and Environmental Studies. And she's also the Associate Director at the Yale Center for Green Chemistry and Engineering. Her research interests focus broadly on green chemistry and engineering, specific emphasis on green downstream processing and life cycle assessment of algal biomass for fuel, and value-added chemical, novel-based bioabsorbents for purification of water and remediation of industrial water. Dr. Zimmerman was previously served as an engineer and program coordinator at the Office of Research and Development for the Environmental Protection Agency. For many of you that know about the P3 award, she was the creator of that award. And you also might know her as an associate editor for environmental science and technology.
Great, thank you. Thanks for coming and having me. I called home this morning and it was 7 degrees, so I told Jim anytime in February you want me to come down, I'm happy to do it. So I'm going to talk to you about water energy nexus. I'm going to talk a little bit about the philosophy and context of that, and then go through a couple case studies recently that my group is publishing. So my first setup for this is really thinking about systems, and the idea is, you know, we're all working on sustainability challenges, but if we're not developing solutions that are in and of themselves sustainable, are we just kind of pushing the ball down the field in terms of more legacy problems later on? So there's lots of examples of this. I'm going to call it doing the right things wrong. And you know, the classic kind of example is using corn to make ethanol, which was actually mandated in the Energy Security Act of 2007. And so thinking now, have we done kind of a life cycle analysis or techno-economic analysis or even some kind of a social assessment, figuring out that using corn to make fuel probably wasn't a great idea. So in terms of land use change, in terms of water eutrophication, in terms of food prices of a global commodity, you know, again, a great goal. We're trying to solve a CO2 carbon climate change problem, but is this really the right way to solve that? Purifying water with acutely lethal substances. So this is a tanker car that still goes by. That's the Capitol building in Washington, D.C. So what's that tanker car carrying? Chlorine, right? Pretty close proximity. Again, here's a really noble goal of purifying drinking water. You know, something we have to do. It's a public health mandate, but is this really the best way to do it? Is this how we want to be transporting it? Is this where we want to be transporting it? Again, doing the right thing, but maybe not in the best way. There's a study that the state of California put out looking at economic development for the state, and a big chunk of it is hanging on the development of new photovoltaics. If you look at the current technologies for this, they're relying on precious, rare, and toxic metals to manufacture these PV cells and get them out into commercial use. And the question again is, yes, renewable energy is a good thing, it's a good goal, we're thinking about carbon, but do we need to use these materials to drive that agenda forward? Doing the right thing maybe in a wrong way. Agricultural crop efficiency, again, if you think about the first green revolution of growing more food, the right thing, but was kind of the pesticide, industrial, agricultural system the right way to drive that forward. Here's one I'm really interested in. Again, this was a policy mandated question. So all of you, I'm sure, know you actually can go into Walmart at this point and buy, or Jim, who doesn't go into Walmart, go into a store and buy a 100-watt incandescent light bulb anymore, right? So that is now banned. And so the policy in that implication again was, let's deal with our energy problem by dealing with lighting technology. Every compact fluorescent light bulb that gets sold happens to contain a little bit of mercury. Is mercury a good thing? What's the toxicity concern for mercury? What's the endpoint people worry about? It's a neurotoxin, yeah? So, you know, you're now telling people, take this thing and put it in your home and hope it doesn't break. And let's take this mercury and kind of spread it out. And better yet, when you're done using that bulb, put it in your car and drive to Home Depot and put it in this bin to recycle it. And if you look at what's going on in these bins, it's a lot like what happens with beer bottle recycling, right? How many people have walked up and smashed it, right? Because you can. And so mercury releases from this system are actually pretty consequential. So we did an analysis that looked at the regional energy grid. So where does mercury come from? From the energy generation, it's from burning coal, right? That's where you have a mercury release from a power plant. All these states that are colored in orange now have more mercury present in their environment from using these bulbs than they would have from the energy at the power plant production stage. So we are again trying to solve a carbon problem by using a neurotoxin, and we're actually putting more out in the environment. So again, this is not the carbon analysis, this is the mercury analysis of this light bulb system. So doing the right thing again, but maybe not in the best way. So how did we get there? These are all really important goals, right? We talked about pure water, we talked about growing food, we talked about producing renewable energy, but is this the best way to get there? The technology, the science is really exciting, right? Photovoltaic chemistry, artificial photosynthesis, it's all really interesting. It's the best of intentions, but we're getting there by doing this. So what's this? Whack-a-mole. Right, you're playing whack-a-mole. So I want to solve this energy problem, and I hit that water thing, and this toxicity thing pops up from chlorine disinfection products. Or I want to deal with my energy problem, and I whack that by going corn-based biofuels, and land use pops up as a problem. So we're going after these things one at a time and being really surprised that there's a relationship and there's a connection. So from a systematic perspective, it's how do you go after all of these things at once? Or how do you at least know ahead of time what these trade-offs might be so I know what moles might pop up next? And how do I get this five-headed hammer to take care of all of this at once? And if you look at the corporate kind of mantra on sustainability, a lot of them will get up and say, I know agriculture is connected to water, and water is connected to energy, which is connected to carbon and climate change. And so my policy for sustainability is I'm going to measure my carbon footprint and reduce it by 10% in the next 20 years. But they don't tell you how much water they're going to use to do that or what toxicity implications are. So they're still, even though they can intellectually recognize that, kind of playing this whack-a-mole game. So what we really need is a new approach, an approach that's based on innovation, right? If the solutions were easy, if they were off the shelf, a lot of them would have been picked up by now, right? Some of them not, right? There's always that story of the $20 bill laying on the factory floor and everybody walking over it because they can't believe there's a $20 bill laying on the floor of the factory. But a lot of the stuff is not there yet. So we need to use innovation. We need new ideas and new solutions. We need to not deal with problems. It's what solutions can we come up with? The only reason to study any problem is to inform its solution, and we really need to start driving ourselves to not just reporting on data and how bad things are, but how is that going to inform the solution to what we're doing. It's important that we do this in a way that makes economic sense, right? That it's going to get picked up. I often tell my students you can make the greenest technology, but if it's sitting on the shelf and no one's using it, you actually haven't had any environmental benefit at all. So we have to make sure this aligns with competitiveness, that it's marketable, that it's feasible, that there's an outlet for the innovations you're creating. This is really about green chemistry and moving from what is circumstantial control. How can you use this chemical? Where can you use it? Here's your NPDES permit. How much of this are you allowed to put out in the environment? To getting towards things that are inherently safer, inherently more benign, inherently more efficient, so that I'm not constantly controlling the circumstances either through energy and engineering or through policy. And then thinking about systematic sustainability. What is that five-headed hammer for whack-a-mole? So I'm going to use water and energy nexus as an example for this. If you look at the curves for these two things, this is from Paul Crutzen's The Anthropocene Era. Looking at, again, these kind of hockey stick curves we see for sustainability. So here's water use from 1900 to 2000 and total energy consumption. So it's not even that we're increasing how much we're using, it's that the rate of that use is increasing. If you look at the interrelationships, it's been pretty well documented and starting to be a lot of data on this, on the amount of water that's used to produce energy, particularly as we move to alternative energy sources like fracking or biofuels, and then how much energy is required. And then Jane, somewhere sitting around here, does lots of work looking at how much energy is embedded in the water we're using. Pumping, distribution, treatment. So, if you look at water withdrawals, about 49% of the U.S. water withdrawals are for the energy sector. 1 liter of biofuels right now, on average, is about 87 liters of water. Shale gas and coal mining, so you're talking about 10 to 16 liters per gigajoule that's being produced. Large-scale hydropower, of course, right? Intimate relationship between water and energy. So right now, about 4% of the electricity use, and then greater than 20% for California because of that water importation, because of pumping. Their electricity is for water production. And then looking at the estimates now on desalination technology, which is known to be a really energy-intensive way of delivering clean, safe drinking water. So there is a connection, there is a nexus, but it's often not looked at for both of these variables to optimize simultaneously. So, we've done a lot of work trying to collect this data that's out there. So this is, if you think about water treatment from the source that we can get it from, whether it's groundwater or surface water, treatment, the distribution of it, and wastewater collection. These are basically all the data we could find for the past 40 years reporting on how much energy is embedded in each one of those steps. So the first thing you notice is there's lots of spread, big error bars, and if you look at these over time, you can start to see which technologies are actually getting more efficient as they're being adopted and used. And you could start to see clusters of technologies fall out, so maybe that's a place we want to invest more time and energy in looking at. Energy footprint of water, again, has been pretty well documented in terms of how many billion kilowatt hours per year we're using for public water supply and in use. And then this is just from supply and treatment. If you look at end uses like heating water for your dishwasher or heating water for your shower, it's almost 3 times as much energy that's used per year on the end use of water than on this supply and treatment life cycle stage. Again, lots of information on water use for transportation fuels. So people are looking at how many liters of water it takes to move different vehicles. This is by grain or corn or soy. And looking at, how many liters when we go from petroleum-based to bio-based fuels, how much more water we're requiring per mile gallon to move these fuels around, to move these vehicles around. Water-related electricity use. So electricity is, terawatt hours per year, and it's about 20% of California's total electricity consumption. And again, this is for moving water into a water scarce place, and delivering that water requires lots of pumping and lots of energy. So if you start thinking about this, the more energy we use, the more water we're requiring, and as energy goes up, then we need more water to deliver that energy, which means we need to do something about water, which is requiring more energy. So there's clearly a feedback loop here about if we can intervene in the system with conservation or efficiency, we can really benefit in both water and energy simultaneously. So the 2 studies I'm going to talk about today, I'm just going to give you a little background on the methodology that we've used. So primarily 2 areas. So one is life cycle analysis using process analysis, which is really base up. So if you think about this house, how much energy went into the bricks and how much into the pipes, into the paint, into the finishes, and actually accounting for every single material and product and energy that's consumed in that house and translating that into an environmental impact. This works really well for small scale systems where we can get a handle on inputs and outputs into the system. It's really data intensive, so you have to get on the phone with Benjamin Moore and find out what they are using to manufacture their paint. It takes a lot of time, and the boundary system is often pretty small. So to complement this for larger scale systems is using economic input analysis. So to actually track the dollars that are spent by a given sector and then translate that into environmental impact. Much less data intensive. All you need is an energy bill. How much energy did you buy? and then using that to calculate how much environmental impact is associated with that money being spent. You get the full system, so the EIO tables are built out for the national economy for the US, so thinking about the connections between every sector. So if the water sector buys energy, the energy sector has to spend money in other sectors to deliver that energy, like steel, and so all of those paths are built out and connected. So our idea is really, sometimes we have this really good data. For some of the larger scale water systems, it's really hard to get that data, and so when do you use process-based, when do you use I/O, and then how do you marry the two to get the most accurate system? The other bit of modeling we do, and I'm really interested in, is this idea of geospatial implications. So LCA, historically, has said you put out this much CO2 into the environment, and that's okay. That's a global pollutant, and it contributes to climate change. When you talk about water quality modeling, that release of nitrogen matters a lot about what receiving body it's going into. And so how do you start taking those inputs and outputs and putting them in a place or a location and understanding environmental and human health impacts? So if you're already in a degraded ecosystem, it might matter more than if you're somewhere that could mitigate those impacts. The other place we spend a lot of time is looking at regional energy grids. So the national grid, like I showed in that compact fluorescent light bulb, is really different. In fact, there's 10 regional electricity grids in the US. So depending on where you are, your energy has a really different carbon footprint, depending on if you're in a place that uses a lot of hydro and nuclear versus a place that burns a lot of coal. So I just put this up as an example. I'm going to come back to this in a minute, but we did a comparison of Tampa right here versus San Diego, California, looking at how much energy is associated with these different water sources. So importing water into California versus doing desalination. And if you look at the regional energy grid, you need to normalize these carbon factors for how much coal and natural gas and petroleum is associated with it. And here's the carbon associated with Florida's electricity grid versus California's electricity grid. So talking about energy isn't enough because I don't really care how many kilowatt hours you're using. I care about the quality of that energy in terms of how much grams of CO2 equivalents you're putting out. So it's not a quantity question to me, it's a quality question of that energy. If energy is free and renewable and non-polluting, do you really care how much somebody is using? And that's a really different philosophy than talking about efficiency. I don't know what I just did. Okay. And then converting this to cost. So it's pretty, interesting to see as you get a more carbon efficient energy grid in California, the cost of that electricity goes up almost $1. Almost $10,000 per terajoule. So there's a relationship here with providing more carbon neutral electricity has an economic cost that's reflected in the market. My computer decided to be not nice. Sorry about that. Okay, so the first application I'm going to show you is looking at environmental and economic life cycle impacts, looking at gray or green stormwater infrastructure. And we were primarily focused up in the Northeast where we have combined sewer systems. So that's stormwater and sanitary waste are introduced into the same sewer system. You have big rain events, those systems overflow, and you have direct discharge of sanitary waste into the waterways. So for this analysis, we wanted to compare, are we better off going in and separating those storm sewers, or are we better off using a green infrastructure technology to manage that stormwater? So gray being separate sewers and green being things like bioretention basins, porous pavement, and green roofs. So the functional unit for this study took us a long time to get to something where you can functionally compare those different technologies. So if you look at most of the state mandates for green infrastructure, this is what their design standard is. It's 1 inch of rainfall generated over a 1 acre watershed. So I need to size my green infrastructures differently. They take different meters squared to provide this storage capacity. And then for the MS4, which is your separate sewer system, they're designed and mandated to handle 10-year storm events. So pretty hard to compare something like this to something like that. So the way we got around this was saying if I had a green infrastructure that managed this much capacity, I have to build that much less storm sewer pipe. And so we actually use that as a credit or an offset. So if I build out this green infrastructure, I can make my separate storm sewer system a little bit smaller. We looked at 4 different cases. So here's my base case, right? So this is what happens right now, like in the city of New Haven. Watershed, the water runs off, it goes into a combined sewer system. That system's supposed to go to the wastewater treatment plant and be treated before it's discharged to the river, but in a really big rain event, we have what's called combined sewer overflow, and then that's discharged to the river. So different water quality between these 2 streams that are introduced out. One alternative said, I'm just going to put in green infrastructure up in this watershed. I'm still going to have flow into a combined sewer system. I'm still going to have combined sewer overflows in really big rain events, but I've gotten some treatment benefit from that stormwater up here using green technology. Alternative B said, I'm going to just take all this water, I'm going to eliminate the CSO, I'm going to have a separate storm pipe, whatever falls in terms of rainwater is going to be directly diverted directly into a receiving body without any treatment at all. And then the last one looked at a combination of these 2. So what if I had some green infrastructure upstream for some treatment benefit before it went through a separate storm pipe and was discharged into the watershed? The next thing we had to do was simulate these rain events. So did it matter if we were in a wet year or a dry year? So we went back into the historical records for the city of New Haven and found, what's the average year in total precipitation? Here's 1970, which was the driest year in the past 100 years, and then 2005 being the wettest year. So we could look at the magnitude of those storm events, the magnitude of that first flush, and then were there different answers depending on what kind of precipitation events you're going to be looking at. Becomes really relevant as we talk about climate change. With more frequent, more intense storms, you want to understand how that system is going to behave and what is now the wet year but might be the average year going forward. So set up a mass flow, right? So we have to do a mass balance. How much rain, how much of that turns into runoff, how much of it goes into a green infrastructure system. So thinking about, can we close the loop and account for all this water that's flowing through the system and where it's going to go? That's the quantity question. The next thing was assigning water quality to all of these flows. So if I got some treatment out of the green infrastructure, what was the quality here versus what went in? So I could account on both a quantity and a quality basis through this life cycle analysis. That turns out to be really important. So I'm putting up this table and there's lots of numbers, but just thinking about what kind of pollutants you might expect to find in storm water. In water quality, here's the raw sewage and combined sewer overflow water quality. Here's what comes out of the wastewater treatment plant. And then if you look at the numbers for runoff, here's typical, right? For total suspended solids, it's at 80. But if you go into the literature, you can find numbers as low as 0.5 milligrams per liter and as high as 4,800 milligrams per liter. So for me, the question in the top conversation with the student is, if this is my uncertainty that's inherent in my system, how much definition can I really get on my life cycle analysis, right? So I'm going to show you the results, and the error bars are pretty big, depending on what the water quality is going into this system. So even if I can get really great numbers on the impacts associated with building a bioretention basin, it turns out that this is a much bigger environmental impact than what it really took me to build out any of that green infrastructure. And then really hard to find numbers, and I met with lots of folks in the lab today who are actually working on this, which is great, but how do these systems actually perform, these green infrastructures, out in the environment? How much of these contaminants are they removing? If you look at the green roof literature, you'll notice there isn't a column here. Green roofs go everywhere from having good treatment efficiency to actually making the water more polluted as contaminants and heavy metals run out of the media that's being used on the green roof to retain that water. So, you can get talk about, I can't even get the order of magnitude, let alone whether I can get the sign right as this plus or minus in terms of environmental impact. So we structured this study so I have fixed impacts, right? Here's all my infrastructure stages. I have to get the stuff, I have to transport it to the site, I'm going to build out my infrastructure, and then I have to maintain it. And then there's a series of variable impacts associated with how much stormwater I need to manage and what's the quality of that stormwater coming in. So we broke this out into two pieces in this analysis. And then it's a pretty straightforward, if you think about LCA, right? So here are my environmental impacts from the materials, transportation, and installation. And then we amortize those over the lifetime of the infrastructure, right? So divide by time. And then here are my variable impacts. What are the impacts from any of the treatment I'm getting, from maintaining that system, and then avoided maintenance I don't need to do on the system that would have been there. So if you think about porous pavement, what are the credits I get for not having asphalt on that site? Okay, so I'm going to show you some results around scenario and uncertainty, cost benefit. We looked at policy, so rather than doing all this stormwater work for those combined sewer overflows, what if I just upgraded my wastewater treatment plant? And then how sensitive these results are. So for endpoints, we looked at all the environmental endpoints. I'm just going to show you data for climate change, so carbon emissions and freshwater eutrophication. It turns out that fossil fuel depletion or resource use trends the same with climate change, even though the orders of magnitude are different, and that all of these water quality impacts all trend the same as freshwater eutrophication. Again, the magnitudes are different, but the trends are the same. So here's carbon, CO2 equivalents. This is fixed impact. So this is just what does it take me to build out this infrastructure, and then here are all the life cycle stages. So it turns out porous pavement has a pretty big carbon footprint, not surprisingly, as you're using concrete and different materials to build this out. And then you'll see this little bit of a credit for not having asphalt that I had to put on that site instead. If you start laying in lifespan, or what's the lifetime expected of these technologies, the error bars get pretty big in terms of how confident I am that if I maintain these systems in a certain way, I'm going to project out and expect to get this lifetime out of them. And then if I add in, you'll see some colored lines. These are the rain events. And rain events don't really have a very big impact because, again, this was just the infrastructure I needed to build out. And so depending on how much rain I'm expecting, that infrastructure had to get built and put in place anyway. Okay, now I want to look at freshwater eutrophication. So here's the nitrogen that's emitted, again, with fixed impacts, with just constructing those installations. And again, you see from porous pavement a pretty high nitrogen loading just from having to get the materials to put that porous pavement in place. The difference with life cycle thinking is, where are these nitrogen impacts happening versus what local waterway am I trying to protect from stormwater pollution, right? So this is where geospatial matters. These nitrogen impacts are felt somewhere else than in the water system that I'm trying to work on. So whose water system am I affecting versus me protecting my water system? And if you think about life cycle analysis, this happens a lot with human health. Whose human health am I protecting at this use stage versus what is all the damage I caused upstream to other people, a societal-based risk to produce that technology? Okay, if I look at variable impacts now, so I'm now allowing it to rain and I'm allowing the water quality of that stormwater to vary. So you'll see all these colored lines. Starts to be pretty big differences in the amount of nitrogen, right, kilograms of, phosphorus equivalents that's being discharged to the waterway, depending on if it's a really wet and heavy rain event or it's a dry year. So these things start to vary, and you'll see that the stormwater, the amount and the quality matter a lot more than the infrastructure that I built out. And the next layer of uncertainty we added to the system was thinking about runoff quality. So here again, you see the error bar for that storm sewer separation go anywhere from almost 0 to almost 30 kilograms of phosphorus equivalents, because what's in that stormwater that's being directly discharged to the receiving body. That has nothing to do with my technology. That just happens to do with what's the pollution that's on the ground during that rain event that's getting flushed and carried out. Okay, so ultimately you want to come up with some kind of cost-benefit analysis. So we said we can have costs in dollars, we can have costs in carbon, or we can have costs in fossil fuel use that we need to use per kilogram of phosphorus that we're removing out of the system. So these kind of lighter gray bars are dollars that I'm spending. How much money am I spending per kilo of phosphorus that I'm reducing from the system? How much carbon am I spending to remove that kilo of phosphorus, and how much oil? And you start to see the answer isn't always the same. So I might spend a lot of money to get a pretty carbon neutral phosphorus removal technology. So in this way, you can start talking to policymakers. If you spend this little bit more, this marginal costs more, it might cost you more, but you might get some benefits in terms of how much phosphorus you're able to remove out of that system for a lower carbon cost. And then the analysis, last bit that we looked at was if I upgrade my wastewater treatment plant. So here's traditional secondary treatment. Here's the total life cycle impacts from that treatment. Here's the direct impacts on the receiving waters. So they're almost the same. And if you upgrade that system to a tertiary system, you can see a reduction from the combined sewer system that reduces the amount of phosphorus that's being released into the waterway. And it's not really costing me that much in terms of the impacts across the life cycle to upgrade that technology. So there's some relationship between optimizing wastewater treatment and optimizing stormwater to get the same benefit in terms of reduced eutrophication out in the receiving body. Okay, and then of course you want to understand how sensitive the system is to some of these variables. So again, here's my carbon impacts of this, and here's how much phosphorus is getting out in the system. And if you looked at, how impervious is this watershed, how much runoff am I going to allow? If I allow that to go up by 10%, here are all those different systems: combined sewer system, bioretention basin, green roof, porous pavement, and then combining them with that separate storm sewer. There's a pretty big jump by allowing the system to become more impervious. So what this says to me is there's an exponential relationship in runoff. The more impervious it becomes, it's exponential how much more runoff I'm going to get out of the system. And it turns out that the more imperviousness you have, the more carbon impacts that you're going to have on the system, and the more sensitive the system is going to be in terms of eutrophication. So again, if I'm a policymaker or I'm a municipality and my system is already pretty impervious, how much is it worth putting in green infrastructure, stormwater management into that system? Am I really going to realize any benefit if there's so much imperviousness there already I can't affect change? So it depends where you are in that exponential curve if you're really going to have any benefit or not in the system. Okay, so from this study, there is some trade-off between, effectively you're buying phosphorus reduction. I'm either spending money, I'm spending carbon, or I'm spending resources to reduce phosphorus. What's that relationship? How do I think about that as a decision maker? And again, if I put a cost on carbon, I can start to normalize all this to a monetary expenditure. There's a lot of implications about what context you're doing this study in. How impervious is your watershed already? How degraded is the receiving water already? And that the more extreme precipitation and increasing land imperviousness, there's very little benefit to actually putting these green infrastructures in to get water quality benefits out. So basically, you should spend your money somewhere else for water quality improvements than doing green infrastructure if you're in this kind of watershed. Okay, and then the second study I'm going to show you is one we haven't published yet and we just submitted. And I guess there's not a lot of time, but I'll go through it pretty quickly. Again, looking at Tampa Bay for where do you get the next incremental bit of water supply from as population grows versus San Diego, California. So it turns out that these two cities are actually look very similar from a socioeconomic basis, from a population basis, and from a water demand basis. So the difference is that in the early 90s, San Diego, California started supplementing their water supply by importing water from outside of the watershed. And thinking about desalination. So there's 3 in design and construction for desal plants out there. And then for water reclamation, they reclaim about 7% of the wastewater from the system. So this is for non-potable use. That's about 22 MGD. But if you look at the opportunity there, they could pretty easily go up to 250 MGD for water reuse. For around here, it's mostly groundwater and surface water. Desalination, obviously the world's largest, is out here. There's more that are being considered, but wastewater reclamation is already up around 28%. So 62 MGD, and there's an opportunity to meet demand for about 200 MGD. So here's the pie charts of what this looks like. So for San Diego, about 81% of the water that's used in the system is imported from outside of San Diego. And for Tampa, it's this mix of groundwater and surface water and reclaimed water and some seawater that's introduced. So there's the big difference, right? 80% of the watershed imported in San Diego, and for around here, it's ground and surface water. The next thing is to look at the regional energy grid. So I already told you there's a big difference in the amount of carbon. If you look at gas and nuclear between San Diego and Tampa, it's pretty similar in terms of how much these two are contributing to the regional energy grid. But if you come down to hydro and coal, so here's California, right? So they're using almost 13% hydropower, and it's 0.01% around here. And they're using a lot less coal, where more is used around here. So that's where that difference in carbon intensity comes from the regional energy grids. So again, we're doing a mass balance on the system. So I have groundwater, surface water, desal water, desalinated brackish groundwater, and then imported water into the system. I have potable and non-potable uses. I have wastewater treatment, and then that effluent can be directly discharged or reclaimed and used in the non-potable water supply. So we set up the same mass balance, and then there's 3 different scenarios you can look at. I'm going to maximize the current supply. What are the alternatives currently being used, and can I use more of it? So can California import even more water to meet future demand? Can you guys use more surface and groundwater to meet demand? The second says, let's maximize seawater desalination. So I'm going to not use any more groundwater and surface water that I'm using now, and all of the new water supply is going to come from desalinated water. And the third scenario said, let's maximize that reclaimed water that's out there, and I'm going to offset whatever supply I can for non-potable use using reclaimed wastewater. So again, I'm going to break this chart down for you, but we're going to look at energy, CO2, and dollars per meter cubed of water that I'm supplying. And we're going to look at energy consumption, CO2 emissions, and energy costs. So the first thing we'll look at is energy. So Tampa's red and San Diego's blue. And it's not a political commentary, I promise. Okay. So the first thing you want to look at is megajoules, right? How much energy is consumed to deliver this water? California has really energy intensive water because I am pumping it from far away and importing it in. So if I go from seawater desalination to water reclamation, Florida, you can save about 0.2% of total electricity use, and in California it's about 1.3%. So again, this is just switching from adding that increased water supply from desal to reclaiming wastewater. And it's just in these 2 cities, right? So imagine if this is a statewide policy. Now, it's really nice that San Diego can save all that energy, but remember, their carbon associated with that energy is much less. So it turns out that the difference in carbon savings by making that switch in California isn't that great of a benefit. So by going from seawater desal to water reclamation, in Tampa Bay, it's about 50,000 cars for 1 year that I can get off, and in San Diego, it's about 206,000 cars that I can take off the road, right, equivalent carbon. So that energy, which was way up here, as compared to Florida, doesn't show up as much on the carbon side because the energy grids are different. And then the last thing is looking at the cost of that energy. So the cost of energy in California is much higher. Again, there's some relationship between having less carbon in the grid and a higher cost for that energy. And so the potential cost savings is about $45 million around here by switching from adding that extra capacity with more desal and going to water reclamation, and $341 million in San Diego. The next thing we wanted to look at is, we had allowed water to change. I said demand from today until the study was done in 2030. How am I going to meet that increased capacity? Not only is water demand going to change, but the makeup of the energy grid is going to change. So California right now, their current grid of renewable energy is about 38%, and by 2030, they have a policy that it's going to be 64% of the energy grid is going to be renewable. So what you're basically doing is saying I'm going to have even less carbon associated with the energy I'm consuming in California. So by reducing fossil fuel in the energy grid by 42%, they're going to realize an 11% carbon reduction in delivering water. So here's this relationship again of, I can save a bunch of energy, but if I'm saving energy that's pretty carbon neutral already, and it's going to cost me a lot of money, I need to make that decision. Do I want to spend that extra money on saving a little bit of carbon in a place like California that's already pretty carbon efficient in terms of energy production? So we're playing this whack-a-mole game, right? So I'm solving my water problem, desal versus water reclamation, and it's costing me an energy and carbon problem. And if you look at the state results that are coming out of California, so here's their energy efficiency programs. Here's their gigawatt hours they're saving annually. Here's the funding they put into it. So basically dollars per annual kilowatt hour, right? To save this many gigawatts is costing them about 22 cents. If I do this through water use efficiency savings, just on the efficiency side, I can save this many gigawatt hours on an annual basis out of the state of California, and it will be 58% cheaper to save it by doing water conservation than spending more money to make their grid more carbon efficient. So again, if I solve these two problems simultaneously, I can solve a water and energy problem rather than spending a bunch of money on the energy grid to get the same savings I would get out of the water sector at a much lower price. So, right, this is whack-a-mole, and this energy thing is popping up, and people are talking about it, and carbon is getting a lot of attention. But the question is, this water thing is going to pop up next. And what we really want this game to look like is this. Right? So when I solve my water problem, it also solves my energy problem, and the moles start beating each other up, so I don't have to play the game anymore. So I'm going to stop there, and I'm happy to take any questions that you guys have on the work that I presented.
Thank you.